Hello and welcome. In this video, we're going to take a look at a concept of antiderivatives, which, is probably what it sounds like. It's the opposite of a derivative. So if you can think about all the rules that you're familiar with for derivatives, primarily things like the basics, power rule, and some of the derivatives of trigonometric functions, how do we reverse those? Can we find a function that has the derivative equal to the function we're looking for? That's the concept. So as far as a definition, a function, let's say capital F, is an antiderivative of a function lowercase f on an interval I if the derivative of capital F is the function f over that interval. Let's take a look at an example. Pretty easy one to start off with. You have an antiderivative of the function f of x equals 3x squared. It's just a matter of thinking, what would you have needed to take the derivative of so that you could get 3x squared? Well, it might be sort of obvious. We've done this many times with derivatives. It's just a power rule. When you have the function x cubed, it will have the derivative of 3x squared. And so that would be an antiderivative. Now, of course, the wording here is a little bit interesting. It's not give the antiderivative. Here the question says give an antiderivative, which would imply that there could be multiple antiderivatives. And remember that anytime we're taking the derivative of a constant, its rate of change is 0. And so its derivative is 0. So another antiderivative could be x cubed plus 1. Or how about minus 5? In fact, any constant here would work. We can represent any constant here as just being plus c, where c can be any real number. And actually, it might make sense intuitively since a derivative gives the rate of change of a function. And all this is the same shape of the graph of x cubed, just simply shifted up or down. You can kind of see this from a graph. And in here, I've taken the graph of y equal x cubed and scale it so it can more or less fit on my page. And then I've just simply shifted it up and down into a couple other very similar looking graphs, but they would all have the same rate of change. At 0, for instance, they would all have the derivative equal to 0. And at 1, then they would all have a slope of 3. The derivative would equal 3. So the antiderivative of a function is really like a family of functions, all with the same shape, simply shifted up or down. Well, we can state this as a theorem. If capital F is an antiderivative of f, our function lowercase f, on an interval I, then the most general antiderivative would be taking that antiderivative and adding any arbitrary constant on the end. So we tend to write just the most basic form of the antiderivative, like in the case of 3x squared, the most obvious antiderivative would just be x cubed. And then we just add c to the end. At this point in time, we can take pretty much our table of common derivatives and reverse them all and take a look at things like the power rule, but going in the reverse direction. Now, the first couple rules we learned for derivatives are pretty easy to reverse, and that might be something where we just use the constant multiple rule or the sum and difference rules. So as it may be expected, if we have a constant multiple of a function, its antiderivative would simply be that constant multiple of the antiderivative of f, and then we just make sure we add that plus c after we've found an antiderivative of f. The same thing with addition or subtraction. We just need to find an antiderivative of f and g, and then make sure that we add or subtract those in the same way that we had originally, and add the arbitrary constant c at the end. One of our most powerful rules, sorry about the pun here, is the power rule. It's x to the power n. And we know how we take the derivative of x to the n, but how do we reverse that process? With x to the n, we know that by taking the derivative, we will multiply by n and reduce the power by 1. So reversing that order and reversing each of those operations, we first need to add 1 to the power and then make sure that we divide by n plus 1. Now, by taking this expression on the right-hand side, if we look at the derivative of x to the n plus 1 over n plus 1, we're going to see that this n plus 1 is going to come down in front and cancel with the n plus 1 in the denominator. And then we subtract 1 from the power, and we should add them with x to the n. Now, this is only going to work for values of n not equal to negative 1. So, what about that case? What if n does equal negative 1? Well, if we're given the function x to the negative 1, we should really be thinking of that as being the function 1 over x. Now, we've seen that by taking the derivative of the natural logarithmic function, we end up with 1 over x as our derivative. But let's not forget that rule over here. But do remember that, the natural logarithm of x is only defined for x greater than 0. But we're looking at an opposite process, and we're starting off with a function 1 over x. Again, it has some restrictions on the domain, but the restriction on its domain here is only x cannot equal 0. And so we should try to get an antiderivative for the function 1 over x that can be applied for the whole real number line except for 0. Try to find an antiderivative that applies to both the intervals from negative infinity to 0 and from 0 to infinity. So what we choose to use here for the most general antiderivative of 1 over x is the logarithm of the absolute value of x. Now I should be adding these plus c's in here for the most general form of the antiderivative. Okay, time for an easy one. Of course, the antiderivative of e to the x is e to the x plus c. And if you want to extend that, for any base b, the antiderivative of b to the x is b to the x over the natural logarithm of b plus c. All right, time to throw in a bunch of trig functions. You have to be a little bit careful about negative signs here. Now, remember the order of differentiating sine many times. Over here, we can see the derivative of sine x is cosine x, and then we take the derivative of cosine x, and we start getting in some negative signs. And if we take 4 derivatives in a row, we end up back at sine x. So looking at antiderivatives, we're going to be starting from the bottom here and working our way up. And these two can definitely be easy to trip up because it's very easy to confuse derivatives and antiderivatives as to when negative signs should show up. So I definitely say it's probably good to draw this little table of derivatives so that you remember which direction goes which. Next come the derivatives of tangent and cotangent. When we're looking at antiderivatives of secant squared and cosecant squared x, we can see tangent x and negative cotangent x plus c. How about secant x, tangent x, and cosecant x, cotangent x? Those ones are also coming straight from the derivatives of secant and cosecant x. Now, while this isn't quite an exhaustive list, it probably is good to also just include the antiderivative of 1 over 1 plus x squared, which is the inverse tangent function, or arctangent x plus c. So just in general, we're kind of reversing all the rules of derivatives, and when we look for a general antiderivative, we don't forget that we have an arbitrary constant. Let's try some examples and start off with mostly the power rule here, a function which is simply a quadratic. When we take its antiderivative, you may expect this to suddenly become a cubic. Well, we'll have to make sure to apply our sum and difference rules as well as our constant multiple rule first. That means since we have 3 terms, we're going to be looking at the antiderivative of each term and keeping the constants 4, -3, and 5. Well, the antiderivative of x squared by raising the power by 1 and dividing is x cubed over 3. An antiderivative for x is x squared over 2. And we've kept this 5 here, but when I think about it, 5 is really like 5 times 1. The antiderivative of 5 times 1 is 5 times x. And once we found the antiderivative term by term, we can't forget to add an arbitrary constant. We can simplify the fractions. And the power rule can apply to any real number other than -1. Let's try another example. Here I've got the function s of t equals 2 root t minus 1 over t. Now notice that the domain of this function would imply that t has to be greater than 0. That might affect how we write our final answer. If we look for the general antiderivative of s of t, then we might want to call it capital S of t. And if we want to visualize root t as being t to the 1/2, we'll have to raise the power by 1 and divide. Now, when you divide by 3/2, it's going to be a lot easier to think about that as simply being multiplied by 2/3. And then, remember the general antiderivative of 1 over t is the natural logarithm of t with an absolute value stuffed in there. The most general antiderivative of 1 over t is the natural logarithm of the absolute value of t. Don't forget the arbitrary constant plus c. And we can simplify. And in the context of our original function s of t, since it's only defined for t greater than 0, we know that the absolute value of t is always positive. And so we could just maybe omit the absolute value and say that a general antiderivative would be 4/3 t to the 3/2 minus the natural logarithm of t without the absolute value plus c. Now, if you wish to think about where the antiderivative might be useful, you might want to think about where we would talk about rates of change. And that pretty much happens in any science or social science, any kind, really. We're talking about how things are changing. And so maybe if you wanted to think of a physical object, we would talk about its velocity as being a rate of change. So, well, since velocity is the derivative of position, position is the antiderivative of velocity. Given a velocity function, we can find out what the position of that object is at any point in time. You can even go one further. If you have acceleration, the antiderivative of acceleration would get you a velocity function, and then an antiderivative of the velocity function could get you the position all the way from acceleration working backwards. Why don't we just try an example of that so you kind of get an idea about maybe where this arbitrary constant has an interpretation as well. All right, well, let's suppose that the acceleration of an object is given by the function a of t equals 3 over root t for t greater than 0. And let's suppose that at a time of 4 seconds, it has a position of 20 meters and a velocity of 7 meters per second. So everything here is in meters and seconds. Let's see if we can find an expression for the position of the object at t seconds. This does involve some concepts from physics that you should hopefully be familiar with, and that's that acceleration is the rate of change of velocity, velocity is the rate of change of position, and that means that acceleration is actually the second derivative of position. And you could write this as s prime, and s double prime, or you could use Leibniz notation. So let's use s double prime of t instead of a of t. That should get us started. Now, when we're looking at the antiderivative, instead of just going to a capital letter, we can get rid of one of the little derivative ticks. And so antiderivative of s double prime of t would simply be s prime of t, or velocity. And here we've got 3 times t to the negative 1/2. So we'll add 1 to the power to get t to the 1/2. And then we have to divide by 1/2. That's the same thing as multiplying by 2. And that gives us 6 root t plus an arbitrary constant. Now we do have some extra information at this point in time that we can use to figure out what that arbitrary constant is. At 4 seconds, we need the velocity to equal 7. In other words, s prime of 4 must equal 7. So we'll plug 4 in and set everything equal to 7, and that should get us our value of c. Let's plug that in before we start carrying on with the process of finding antiderivatives. In this case, we haven't found a general antiderivative. We found the particular antiderivative for the application of this problem. Now we can go ahead and redo this one more time to get another antiderivative for position. And we've seen the antiderivative of t to the 1/2 is 2 over 3 times t to the 3/2. We've seen that the antiderivative of a constant is simply the constant times t. And then we'll have to add another plus c at the end. Now, if you want to be a little bit more careful, we shouldn't probably use plus c again. We should probably look at a different letter. And if I already used c for constant, maybe we should use k because it kind of sounds similar. But feel free to use your favorite letter other than s or t. Now we can simplify this, plug in the value t equals 4 and set it equal to 20 to solve for k. That gives us k equals 8, and we can plug that in to get the expression for position. And the position at time t is simply 4t to the 3/2 minus 5t plus 8. And you can double check by taking the derivative of this twice that you should end up with 3 over root t. And you should also see that we've chosen the values of c and k so that we end up with a position of 20 meters, a velocity of 7 meters per second at 4 seconds. And so really, if you want to look for an antiderivative, in general, it'll have a plus c. But in the context of some applications, we can give the particular antiderivative that's applied to our problem. All right, so that kind of gives you the general idea of an antiderivative. It's reversing the process of the derivative. We have a general antiderivative or we have a particular antiderivative. And that is going to tie in with our area problem, surprisingly. We have one important concept coming up, the fundamental theorem of calculus, that ties together the branches of differential calculus with derivatives and integral calculus, which currently sounds like an area problem. Putting those two pieces together is vital, and that is why it's called the fundamental theorem of calculus. So stay tuned. Thanks for watching, and I'll see you in the next video.